Okay, so I'll just let you guys read through this and try to do number one. And yeah, today I'll give more freedom just for people to work on the problems and try to develop the theory on their own. So well, I guess it'd be worth talking about it too. So, yeah, so AMGM is one inequality. There's also QMAM, or quadratic mean arithmetic mean. So this quantity, well, let me just first copy this over. So this quantity is called the root mean square, or the quadratic mean. And it shows up in chemistry for like particles of maybe like some constant related to gas particles in a vacuum. So quadratic mean is just the square root of the average of the squares. So and yeah, so we're going to prove that QM is greater than or equal to the arithmetic mean. And I guess we want to do it for all reals and not just non-negatives. So we want to prove this statement basically. So I'll give you guys some time to think about it. Do we always prove inequalities by induction, or is there a more foundational way to derive them? I don't think induction is a very common way to prove inequalities, to be honest. So we did use like Cauchy forward-backward induction for AMGM, but a lot of the other ones, they're kind of built off of AMGM or Cauchy Schwarz. So sometimes yes, but not usually. Usually you prove inequalities by using theorems like other inequalities, some of which are not proved with induction. And today we'll also talk about a different way to prove AMGM, which we'll use Jensen's. Okay, so how can we go about this, right? So this is the AM. Well, let's just do it for like 3 variables and just kind of see what it looks like, right? So the quadratic mean of 3 variables is bigger than or the arithmetic mean. And you could try it for some numbers, like let's see if it's true for like 3, 2, 1, right? 9, 4, 1, 3, 2, 1. Is this true? Let's see. So 14 thirds bigger than 2. Is that true? Yeah, wait. Well, so this is Okay, yeah, that's true. Sorry, I had a brain emptiness moment. Yeah. So, okay, it seems okay for that triplet. But yeah, so what might we do? What's the ugly part of this inequality that we'd like to get rid of? Oh, wait, do people see the writing on my screen? Hang on, I think I should reshare my screen for those who arrived late. My bad. I don't know if does everyone see my shared screen? Okay, great. Okay, so apparently if that's weird, that's like a bug. Usually if you join a Zoom meeting late, it just lets you see my shared screen, but I think they updated Zoom and now there's some bugs. Okay. Yeah, so Drita said square root. Yeah, maybe we want to get rid of the square root, right? So let's square both sides and see what happens. And so and let's multiply through by 9. Now, how can we see this is true? This is going to be annoying if people arrive late and I have to unshare and reshare each time. Okay. Okay, yeah, so someone else. So how can we see that this is true? Let me reshare and unshare again, just so everyone can see it. PDF. Oh, and you should keep yourself muted, especially if you have background noise. Just gonna... So someone suggested move everything to the left side. Yeah, we can do that. So you know, a squared, b squared, c squared will cancel. So if I move everything to one side, I'll have so yeah, why is this true? I'll give you a hint. You can make it the sum of 3 different things. I don't think you can use a plus b plus c quantities squared. Yeah, so we can use a and gm 3 times with it, or we could just write it like this is just a minus b squared plus b minus c squared plus c minus a squared. So, you know, you'll have an a squared and an a squared. That makes 2a squared, and you'll have things like minus 2ab. And then each of these is a square, so they're all non-negative. So the sum of 3 non-negatives is non-negative. Okay, so then we can reverse our steps and, you know, get the original. And the good thing about this is that a and b don't even have to be positive, I guess, right? If we use AMGM, well, you know, you can do casework and you'll see that negatives will work too. But in general, AMGM doesn't work on negatives. Here, because we have an a squared, you know, like we'll have things like a squared plus b squared greater than or equal to 2ab. And this is true even if one of a or b is negative. So that's fine. You can just do casework on how many of them are negative. Okay, so yeah, this generalizes to n variables. So we can prove QM with just AMGM. Or this is like a sum of squares. So I'll call it SOS, sum of squares. But really this part, it's the more intuitive way is to rewrite this part as like a squared plus b squared plus c squared times is greater than 2ab plus 2bc and so on. So let me write it more properly. So basically we're adding this. This is true by AMGM, and then this, and then this. So we add those and we get the desired inequality. And each of these is true by AMGM. I think maybe earlier I was sharing my display and not my screen. So maybe I don't need to redo this each time. Okay. So. And then we can reverse our steps and get back to the QM-AM inequality. So far we have the quadratic mean is bigger than or equal to the arithmetic mean. It's bigger than or equal to geometric mean. So for two variables, this would look like quadratic mean bigger than or equal to arithmetic mean, bigger than or equal to geometric mean. So there's also the GM-HM inequality, which, so the HM is just the sum of so the harmonic mean is the sum of the, I guess the reciprocal of average of reciprocals of n numbers. So like for 3 numbers, it would be you average their reciprocals and then you take the reciprocal of that. So it's 1 over that. So it's usually written like n over 1 minus a1 plus dot 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 1 over 1 over an. So that's HM, the harmonic mean of n numbers. So let's see if we can prove the oops, no, not this one. Let's see if we can prove the geometric mean harmonic mean inequality. I'll give you some time to think about it. And notice these are for positive reals, not non-negatives or like all reals. So part A says, which mean does the harmonic mean resemble the most? So out of the 4 means we've talked about, which one does the harmonic mean resemble the most? It doesn't quite look like the geometric mean. That's a product. And the quadratic mean actually has some squares in it and a square root. So probably the harmonic mean is closest to the arithmetic mean, right? Just like in terms of the algebraic form of it. So let's see if we can, how can I manipulate this to look like AMGM instead of GMHM? AMGM and reciprocate. Start with the reciprocal right-hand side, that's AM. Yeah, so, these are positive numbers. All the numbers are positive. So we don't have to worry about multiplying by negatives, right? So we're allowed to like multiply both sides by an expression and not worry about if it's negative or not, and flipping the inequality sign. So this is like sum of all of these things. And then I'll divide both sides by n. So I'm multiplying by this, and I'm dividing by n on both sides. And then I'll divide by this, the nth root thing, right? So I'll divide by the nth root on both sides. So this is just, regular algebraic manipulations. So yeah, why is this true? Yeah, right. So Alan says you can do AMGM on the reciprocals and take the reciprocal of that. Yeah, so now this is just true. This is just AMGM on the variables 1 over x1, comma 1 over x2, dot 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 1 over xn. So we do AMGM on all n of these terms and we're done. And then we just, multiply both sides by this and divide both sides by this and multiply both sides by that. And we get back to what we want to prove. Okay, so it turned out that AMGM kind of implied both GMHM and QMAM. So we have this like mean chain inequality thing, right? So QM greater than equal to AM greater than equal to GM greater than or equal to HM. And this is true for positive reals. All variables are positive. So, and this is true for any integer number of variables. So one interesting thing is like, if we look at the expressions, right? They're all of the form like, so this is 3 variables. This is, well, the AM, and then GM, and then HM. So they're all like of this form. I don't know if someone's, well, except for GM, they're all like A to the P. P isn't prime, it's just like some positive real. B to the P, C to the P, right? Over 3, the number of variables, to the 1 over P. So this is, that over 3 to the 1/2. This, no, to the, yeah, so P is 2. This is when P is 1. When P is 0, this is undefined. But by convention, it's just defined to be the, when P is 0, this like f of P is defined to be just the geometric mean. So you take the product of the n numbers and you take it to the 1 over nth power. So the geometric mean. And then this is, basically a to the -1 plus b to the -1 plus c to the -1 over 3. And then you take it to the -1. So that's when P is -1. So, we can do this for any number of variables. I just did 3 as an example. So, and so this would be sum of AI to the P, I equals 1 to n. And you divide by the number of variables and take it to the 1 over pth power. So this is, it turns out, like if P is greater than or equal to Q, then f of P is greater than or equal to f of Q. So, if we did P of like 1.5, it would be between the QM and the AM. So QM is when this function is like 2. AM is when it's 1. GM by convention is when it's 0. And whatever it's called, HM is when it's -1. but it doesn't like, this is true even for like, so HM is bigger than like when it's -2 and so on. And this is true, this is, bigger than when it's like -2.1 and so on. Yeah. So it's a, as P decreases, I guess it like decreases, or it decreases monotonically or stays the same. There should be a name for this. I just don't remember it. Let's see. Is there a name? Yeah, you guys can probably search it up on Google faster than I can, so I'm not going to worry about it. But I think it's related to the LP norm of things. So the LP norm, I think it's like the same thing, but I don't know if the LP norm has like the normalizing factor. So I think what the LP norm is like for the distance function in two variables, right? You do Pythagorean theorem, and that's the distance between like 2 points. But you can also do like other notions of distance, like the taxi cab distance, which is like this between 2 points x1 and y1. Sorry, this should be a minus sign. And you can normalize the distance function. And then it becomes, this f of p function. So this would be like the L1 norm, I think. L2 norm would be like, so if you have 2 points x1, y1, and x2, y2, you can define different notions of the distance between the 2 points. So this would be like the normal L2 norm, which is our Euclidean distance. So the 1/2 power. And then the L3 norm would be, just with the 3. And this can be generalized to any number of dimensions. So, so this looks really similar, but whoops, that should be this looks really similar, but we're missing like a divided by 2 or something. So basically, LP norm is the change in the first variable plus the change in the second variable. And if it's an n-dimensional vector space, then you'll have something like n coordinates for each point, and you take it to the 1/nth power. But I think you can do like a normalized LP norm where you kind of like divide. This is optional, but if you divide it by n, then it's kind of like the same thing that we had above. So it's kind of like the normalized LP norm is decreasing as P decreases. So it's monotonically decreasing. So f of P is, which means that like if P is greater than or equal to Q, then f of P is greater than or equal to f of Q. So it can stay constant. That's constant functions are also monotonically decreasing by this definition. It's not strictly monotonically decreasing, it's just monotonically decreasing. So constant functions fall into this category of monotonically decreasing, but yeah. So this is kind of interesting because this is like just a special case of that. And I don't know how to prove it. I guess you would need some analysis or some, college level math to prove it. But yeah, you can view QM, AM, GM, HM inequality, the mean. So this is called the mean chain inequality. You can view it as a subset of that more general phenomenon. Is it monotonically increasing? Yeah. Okay, yeah, you're right. I don't know why I'm thinking this should be increasing. So yeah, as P increases, the f of P increases. My bad. Yeah, I don't know why I said decreasing. Yeah, it should be increasing, my bad. So I think somewhere else I wrote decreasing too, or I said decreasing, but I should have said increasing, yeah. I meant, yeah, my vocabulary was just wrong. What I wrote is right, but yeah, as P increases, F of P increases. And usually, you know, it's as P as the input variable increases, what happens to the output function. So yeah. Okay. So we don't have to do problems with that, although there are some problems at the end, but I think these are just kind of subsets of things we've already talked about though. So we'll just talk more about the theory. So, I guess let's talk about Cauchy Schwarz. So I always like, checking if things are actually true. So, Cauchy Schwarz says if you have two sequences or two vectors, then hang on. Yeah, it says that. So for instance, if I have like 1, 3, 5 and 2, 3, 4 are my two sequences, or maybe 2, 4, 3 is fine. So it would say that this plus this plus this plus this plus this is greater than or equal to basically the dot product of the sequences. So, and then you square that. So let's see if this is true numerically for my example. So this would be 29 squared. Okay, that's true. So, in general, if you have I think the best way to look at it is with a geometric interpretation. So I guess you could sort of prove it this way, geometric interpretation. So basically, you can think of these as n-dimensional vectors. Think of AI and BI. So, A1 dot dot to AN and B1 dot dot to BN as two n-dimensional vectors. And then what it basically says is like, when you do the sum of the squares here, this is like the square of the magnitude of the vector, right? So the magnitude in 3 dimensions would just be, the distance from 0. And in dimensions, it would just be, like if these are the coordinates, it's just this. So basically, Cauchy Schwarz is if you have vectors A is A1 dot dot to AN, and B is B1, B2 dot dot to BN, those are the coordinates, then it just says the magnitude squared times the magnitude squared of B is greater than their dot product squared. So, you can check that this is correct. Like this is what the geometric interpretation is. So, this is the magnitude of A1 squared. I mean, the vector A squared, this is the magnitude of B squared. And this is the dot product. And you can prove that the dot product is this by law of cosines. So this thing in parentheses is the dot product of vector A and vector B. So the dot product is, there's two equivalent definitions of the dot product. One is that the dot product of a vector and another vector is, if you're given the coordinates, it's like in some basis, it's just like A1, B1 plus A2, B2 plus AN, BN. The second definition is that it's the magnitude of A, magnitude of B, and then times the cosine of the angle in between the two vectors. So, this is just true by law of cosines because, you can check that, let's say for 2 dimensions, let's say we have like A1, A2, B1, B2. If you just do law of cosines on this triangle and this is 0, 0, then you'll get that, the two definitions are equivalent. So, this is law of cosines. If this is theta, then basically, you'll have like so law of cosine says the vector A squared plus the vector B squared. Those are the lengths of these two sides of the triangle minus 2AB cos C. Cosine theta is, so this is the vector so this is A and this is B. And you just subtract. So the vector A minus vector B is the blue arrow, and that's like magnitude squared. So in coordinates, this would be like A1, A2. So squared. And then the x coordinate plus the y coordinate squared. X squared plus y squared of the second vector. And then minus 2AB cos C. Cosine theta is equal to, so then, we can just like do the distance formula here. So the difference between the x's and the difference between the y's. B2 minus A2, A1 minus. So, this is a digression on like equivalence of the dot product. Of dot product definitions. So then when you square this out, you'll have B1 squared plus A1 squared plus B2 squared plus A2 squared minus 2A1 B1 minus 2A2 B2. So I should probably not write too far on the left, but this is the left-hand side. The left-hand side and the right-hand side cancel that out. Those cancel out and those cancel out. And then you just divide by -2 and you get that this definition of the dot product is equal to this definition of the dot product. So yeah. So both of these are denoted, it's denoted A dot B. That's the dot product. And this generalizes to any number of dimensions. Like it can be an n-dimensional vector, not just a 2-dimensional vector like I proved here. Okay, so that means the other way we can write this is that this is like A magnitude, B magnitude, cosine of the angle between the two vectors at their tail. So, this expression was equivalent to this expression by the law of cosines thing we just did. And then it says we square it, and that's bigger than, this. So yeah, what does this say? Well, this just says if I divide by A squared, A magnitude squared and B magnitude squared, this says that cosine squared theta is less than 1. And that's true. So all this is saying is that, the dot product of two vectors is at most the product of the two vectors of magnitudes. So Cauchy Schwarz, when interpreted geometrically, just says this. That's all it says. I mean, well, you square it basically. So Cauchy Schwarz is equal to this thing. So this is geometric interpretation of Cauchy Schwarz inequality. And of course, cosine is between -1 and 1. So, so when you square cosine, it's less than 1. So that's a true statement. So when does equality occur, right? Well, equality occurs when cosine of the angle between the two vectors is 0. I mean, when it's 1, so theta has to be 0 radians. So cosine theta equals 1 is equality case. And that's when theta is 0. And when theta is 0, the two vectors, they're pointing in the exact same directions in n-dimensional space. So that means one is a scalar multiple of the other. So if one has like coordinates 1, 2, 3, then the other has coordinates like 4, 8, 12 or something. So like one vector is a multiple times the other vector. So A is a scalar multiple of B as a vector. So that just means all the coordinates, like A1, the first coordinate of vector A divided by the first coordinate of vector B, equals this, equals ... equals an over bn. So that's the equality case of Cauchy Schwarz. And this is true for any real numbers, not just it's not just positive real numbers. The vectors can have negative coordinates. So I'll just abbreviate Cauchy Schwarz as CS. So this is just some constant. It can be a negative constant. Okay. So, that's like the high level geometric interpretation of Cauchy Schwarz. You can also prove it by like showing that the discriminant of a certain quadratic is I guess negative, so it has no real roots. So the quadratic is above the x-axis. And maybe we'll come back to that. But yeah, well, how about you guys can try to, so we should also prove it a more basic way, I suppose. You can try number 1, number 2, and number 3, and I'll take a break from talking for a little bit. So I'll just say a few words on number 3, like the generalized triangle inequality. It's like one of the most important inequalities in mathematics, just like Cauchy Schwarz. And it turns out you can prove it with Cauchy Schwarz. So, why is this the generalized triangle inequality? Well, it's just saying that, oh, I don't know why this is plus signs. I don't think this should be. Yeah, I think there's a typo here. I think these should be negative signs. So I think this should be negatives. Yeah. So this is just saying the magnitude of a vector x squared, I mean not squared, plus the magnitude of y is greater than or equal to like the magnitude x minus y. So if you think about it as vectors in 2D or something, if this is x and this is y, then x minus y is the blue vector, and its length should be less than the sum of the other two red sides. So geometrically, that's triangle inequality, but it's often useful to use the algebraic version of triangle inequality. And also the complex, like you can also interpret it as complex numbers, and there's a version of triangle inequalities with complex variables, which is also useful. But yeah, I'll let you guys try to do number 1 and 2 and 3. And then we'll talk about it after I rest my voice a bit. Oh, so we're just working on number 1 and 2. Actually, I'll just work on number 1 without talking. Okay, so we want to prove this, so we can just expand it out. And so let's see. Some terms cancel, like this one and this one. So we just need to prove that so yeah, why is this true? My mic is close enough to me for me to be heard well. Yeah, this is just AMGM on these two terms. Okay, so that proves the 2 variable case. Let's look at the n variable case suggested right here. So we have this weird quadratic thing. This is a quadratic in X. So it's in the form, let's say, like capital AX squared plus capital BX plus capital C. So capital A is going to be all the X squared terms, right? So it'll be like sum AI squared. Capital C, it's going to be all the constant terms. So it'll be like all the B terms squared added together. And then capital B, it'll be like all the linear terms coefficients. So negative 2AI BI. So, okay. So, this thing, well, on the one hand, it's greater than or equal to 0. Each term is greater than or equal to 0, right? So graphically, it's like we're adding all these functions. Like we have all these quadratics. This is a quadratic. We add it to this quadratic. We add it to this quadratic. We add it to this quadratic. And this has roots at like B1 over A1. This second one has a root at B2 over A2. The third one has a double root at B3 over A3 and so on. So when we add these up pointwise for each value of x, then clearly like when we add up all these positive quadratics, each x coordinate will be positive, right? I mean, the function is pointwise positive, because if I add, this point to this point, the output would be like right there or something. If I add this point to this point, the output would be right there or something for that value of x and that value of x. So, okay, it clearly has no real roots, right? But there is one case where it can have a real root. Can anyone see when that would be? So if the diagram looks like this, it'll have no real roots because it'll be all positive and there will be no like x-intercepts of the whole quadratic. Well, not when all. Yeah, that's not quite right, Cayenne. When AI equals BI, that's one special case of the equality case. So we would need all of these terms to be 0, right? Like this has to be 0, this has to be 0. So basically when A1x minus B1 is 0, so AIX minus BI is 0. So that would mean x has to be BI over AI. So that means like for each value of index I, for each value of I, B over A is constant. So B1 over A1 is equal to B2 over A2 and so on. And you can see it in this quadratic, right? That's when all the terms are equal, is when each A coordinate is a constant K for the same times of the corresponding B coordinate for a constant K. So this is K. Okay. So yeah, that would be the picture when all the quadratic functions we're adding, they look like this, right? They have the same double root when all the quadratics all have the same double root. So then you can have one real root and only one real root. And then all the other points on the functions, when you add up these quadratics, is like a positive number. Okay. So this has, if it has, so the discriminant is defined of a quadratic is defined to be like b squared minus 4ac. It's the thing under the square root sign. It's also defined to be the difference between the two roots squared. And that's how you define it for cubics and stuff. But for quadratics, the discriminant is b squared minus 4ac. So this thing, in the quadratic formula, it's like negative b plus or minus b squared minus 4ac. So if all the roots, if we have 0 real roots or no one real root, because all the terms are positive and there are no, or at least at most one x-intercept of the quadratic, then that means the discriminant is negative, right? Or non-positive. Because if this is a positive number, if this is positive, then there are two real roots, because we have negative b plus or minus a positive number. So that'll be two real roots. but there are no real roots, or at most one real root based on what I said here. With the graphs and adding up the quadratic graphs. So that means the discriminant can be at most 0. So we have to have b squared is less than or equal to 4ac. So, what was b again? B was all these terms, bi, and you sum over it for all I. And then b squared is supposed to be less than or equal to, let me write 4ac down here. So 4a was like the sum of the a's terms. C was like the sum of the b terms. So, okay, so if I square this, I'll get basically Cauchy Schwarz, it seems like. So if I divide by 4, I'll get that ai, bi, sum over all I squared is less than the sum of the a squared times the sum of the b squares. And that's Cauchy Schwarz. Cauchy Schwarz is proved by that. Okay, yeah, does that make sense? Okay, you can feel free to ask if there are questions, but maybe we should just, let's see. So let's skip the triangle inequality for right now. It's not super critical at this point. We can look at, yeah. So let's take a moment and see if you can do, you don't have to tell me, but maybe it'd be good to try some of these problems on your own. You can do them in your head if you're familiar with Cauchy Schwarz, or you can write it down. But yeah, see if you can use Cauchy Schwarz to prove QMAM and AM and AHM. So I'll go ahead and do number 1, or talk us through it. Okay, so we want to prove the this thing. So just like last time, we should get rid of the square root first. So what can be our next step? Consider one vector. I think I know what you mean by that, but can you elaborate? Consider one vector. So let's multiply by, yeah, so a vector with all ones as the components. Yeah, so we can multiply by n squared. And this doesn't quite look like Cauchy Schwarz just yet, but there's a different way we can interpret the n, right? Which is that, well, this n, it can be a 1 plus 1 plus, so it's n ones. So then, this is true, because if we think about it, then basically one sequence is all ones. The other sequence is A1, A2, dot dot dot, AN. So when I take their dot product, it just looks like A1 plus times 1 plus A2 times 1, the plus dot 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 AN times 1. So that's just the sum of the variables. And then this is the magnitude of one, and this is the magnitude of the other one. Squared. Okay. So that worked out fine. So I think, you can probably do a lot of these on your own. So maybe let's look at 7 together. You can do a lot on your own after class. Well, I'll just leave the page up here, and you can work on whichever problem seems interesting. The one I want to talk about next is 7. So if you want to go along with what I want to talk about, you can try 7. So let's see if I can figure this out on the spot. So all the coefficients are positive. So maybe P of X is like So we want to somehow combine P of X and P of 1 over X, right? So because all the coefficients are positive and we're checking it at when we're plugging in X equals 1, let's just like kind of multiply this over for, it's holds for all positive X. So yeah, we don't have to worry about a negative sign. So let's just multiply through. So this is greater than or equal to 1. So if this is true for X equals 1, then it's true for all X that is positive. That's what we want to prove. So this would be like so, this is equal to P of 1 over X and P of X. So what if we applied Cauchy Schwarz on maybe these two terms? What do we get? So let's see. This is the right-hand side. I mean, the bigger side of Cauchy Schwarz. So, basically we're letting one of them be like square root this and square root that. So these are the coordinates. So, basically it would just be like an root an times root an and root an minus 1 times root an minus 1 and so on. So it'd just be an plus an minus 1 plus, because this part will cancel this part when we take the dot product, and this makes those are the squares of root n and root n, root an and root an. So this whole thing is greater than or equal to this thing by Cauchy Schwarz. But this thing is just exactly P of 1. Because we're plugging in X equals 1 is to get the sum of the coefficients. So because this is a true statement when X equals 1, then it should be true for all positive X. By Cauchy Schwarz, I suppose. Like when we apply Cauchy Schwarz, so let's see. So we need to prove it's bigger than 1. Hang on. So sorry, this is hang on. Yeah, sorry, I forgot to put the square on the dot product thing. So this is square. So why is P of 1 bigger than 1? Yeah, the X is kind of, well, the X to the n cancels the 1 over X to the n. Because, basically what we're saying is like, let's say the sequences are like x1, like dot xn, and 1 over x dot. Well, really what we're saying is like the sequence is square root an x to the an, and the second sequence is square root an over x to the n. And then the second term would be this in the first sequence. So in general, the nth term is ai over x to the I square rooted. So those are the two sequences. So when you apply Cauchy Schwarz, you take the dot product of the two sequences. So when you multiply this by this, it'll cancel. Okay, yeah. So the original statement, it says if I plug in x equals 1, then this is true, right? So P of 1 times P of 1 is greater than or equal to 1. So P of 1 squared is in fact, greater than or equal to 1. So that means this is greater than or equal to 1 right here. So we have that this thing by Cauchy Schwarz is greater than or equal to this thing. And this is exactly P of 1 squared, which is greater than or equal to 1. So, and that's what we want to prove. So this is true by, for all x now, by Cauchy Schwarz. Okay, so I don't know if I explained that well enough. So this was in the Thomas Mildorf handout. So I'll just copy that over too. So you can look at a better typed out solution. So, there are lots of things that are, good to talk about for Cauchy Schwarz, but yeah, one common form of it is like the last bullet point here. So I think this is called T2's lemma, but it's just Cauchy Schwarz in another form. If you read the last bullet point here, sometimes it's useful to use Cauchy Schwarz in this form. So here the sequence is like square root x1, y1, square root xi, yi for one sequence, and like square root xi, yi divided by yi for the second one. So the sequence is AI is like xi, yi. Bi is xi over yi. And then when you take the dot product, sum AI bi is sum of like so that equals xi for each term I. So I think it would also be interesting to talk about, let's say we have, yeah, I'm just gonna say, so there's something called Jensen's inequality. So I guess it's pronounced Jensen. So this says if you have a convex function, then let's see. So the picture goes like this, maybe. So let's just do it for like 3 points. So if you have points on a convex function, then so yeah, I have to draw the picture to remember how it goes. So let's just do it for 3 variables, for instance. Then this is true. So let me define what a convex function is. So convex just means like if you connect any 2 points on the function, then all points on this line segment lie above the function. If the function happens to be twice differentiable, then you can say that f of x is convex if the second derivative is greater than or equal to 0. But convex, it doesn't have to be a differentiable function. It can be like a weird function with non-differentiable points. And it can be like, it doesn't have to be strictly convex either. Like I guess a flat line might be convex. So if it's twice differentiable, if the second derivative exists. So on Olympiads, a lot of the times they are differentiable functions, but the concept of convexity has nothing to do with like it doesn't have to be a differentiable function. Most functions are probably like not differentiable that are convex. So yeah, so why is this true? Well, we can see that this is true because it's kind of upward pointing, right? So if it's a nice, smooth, like differentiable function that's convex, then here, let's say we have coordinate axes, right? So B, C, A. This is A comma F of A. This is B comma F of B. That's the coordinates. So, and this point is C comma F of C. That's the coordinates. So, basically what this says is like the centroid, so the average of these 3 points. So, if I draw in this triangle, right, and I draw the centroid, then the centroid will have so the centroid will have x coordinate A plus B plus C over 3. And the y coordinate will be, the average of the y coordinates. So that's the coordinates of the centroid G of these 3 points B, A, and C. What this says is like this centroid, its y coordinate is greater than the y coordinate of if I just plugged in the average of A and B and C into the function and found its y coordinate. So the fact that, point G here has a bigger y coordinate than point, let's just call this H here. That's kind of like the idea behind why Jensen's is true. So there's also, if it's concave, meaning if it's convex down, like concave down. So if it looks like this, then the inequality is flipped. So everything, all the inequalities are flipped. So here it would say like f of A plus f of B plus f of C over 3 is less than or equal to f of A plus B plus C over 3. So, one application of this is we can prove AM GM with this. So I think the idea is we can so let's do AM GM proof. So, let's say f of x is like ln x. So the log, or you know, you can just write it log x, and it'll probably mean log base e. So the logarithm function, it looks something like this. So you can check that it's like concave down. So that means the second derivative is not positive. Let's see, the derivative is 1 over x. The second derivative would be like 1 over x squared times a -1. This is f prime of x. This is f double prime of x. So this is you know, less than or equal to 0 for all x and all x positive, because this is only for x positive, because the ln function is only defined for positive x. So we can see that, you know, the second derivative is negative, so it's concave down. This is log x. So if we apply, you know, if we apply Jensen's on this function, let's see what we get, right? So let's see, how does this go? So f of so this is less than, because it's concave down, meaning every line segment connecting 2 points is, you know, below the function. So this is less than f of the average of the points. So, okay. So, you know, f is just the logarithm. So I'll just write ln for brevity. Okay. So then this is, let's see. Well, we can use properties of logs, and this says ln of, this is 1 over n, ln of the product of all the positive numbers a1 to an. And then this is just ln of a1 the dot times an to the 1 over n by another property of logs. And then this is less than ln of the arithmetic mean. So, you know, these are all positive. So we can take e to both sides. And that cancels out the ln. So then this is AMGM. So yeah, I guess AMGM is like a special case of Jensen's. So yeah, this is pretty cool. So that's like the third proof of AMGM. So somehow it's kind of like, you know, when you squish the points closer and closer to each other on the curve of the ln function, then the inequality, you know, becomes more like the two sides get closer and closer together. Hmm. Okay, so let's do one last problem for today, which is gonna be, so sometimes it's good to look at equality cases of inequalities, and it can tell you something. So let's take a look at this. Yeah, anyone have any thoughts? Okay, so Sunana said Cauchy. So yeah, how can we use Cauchy here? So Drita says, yeah, for Cauchy Schwarz. Okay, so we can let our sequence be A, B, C and X, Y, Z. Okay, so if we apply Cauchy Schwarz to these two, what do we get, right? So this says 25 times 6 squared, 36 is greater than or equal to this expression, right? Yeah, so Alan says the equality case gives one solution. Yeah, so we would have, oh, this is exactly 30, right? So 5 squared times 6 squared is greater than equal to an expression that happens to equal 30. Oh, squared. This is squared, my bad. So this is the equality case of Cauchy Schwarz. So that means that what must be true about these two sequences, A, B, C, and X, Y, Z. So let me just type what I just said. This is the equality case. Okay. So what's equal? I see some people saying equal. What's equal? What do you mean by they are the same? Can you be more specific? Well, no, it doesn't mean so it doesn't mean that it doesn't mean A equals B equals C, and it doesn't mean X equals Y equals Z, and it doesn't mean A equals X, B equals Y, or C equals Z. It doesn't mean either of those two things. So what it actually means is like the two vectors or the two sequences, like basically you have these two vectors, right, in three-dimensional space. One is a scalar multiple of another, not a permutation. Yeah. So that means like, if the coordinates of one are like 2, 3, and 4, then the other ones are like 2k, 3k, and 4k for some constant k that's real. So what it means is if I divide the corresponding exponents, like 2 over 2k equals 3 over 3k equals 4 over 4k equals 1 over k. Like this should be a constant. So like A over X equals B over Y equals C over Z. So 1 is like, if this is 1, 2, 3, then this could be like 2, 4, 6 or 3, 6, 9 or something. So they can be different, just that one sequence is like a multiple of another. It's a scalar multiple of another. So that means that what we get is that, so conclude at the end that A over X equals B over Y equals C over Z. But then, if these are all the same fraction, how is this fraction related to, like, let's say this fraction? So, let's say I have some fractions, right? 1/2 equals 2/4 equals 3/6. So how does it relate to this fraction? Are they equal? Yeah, it turns out they're equal. So, you can think of it like this, right? So let's say you have A over X equals B over Y. You want to prove that this implies that if you add the fractions, that this equals this, right? Equals this. So we want to prove this equality. Well, if I want to prove this, you can just do it by rote. So A, if I cross multiply, A plus B times X equals A times X plus Y, right? And then you'll just get AX plus BX equals AX plus AY. So the AX cancels and you get BX equals AY. So then you get A over X is B over Y. And this is a true statement because that's what we started off with. So you can reverse these steps and prove that this is also true. And then you can repeatedly apply this. You can apply this to get this equals this, equals this. And then the first fraction also equals this. So then you can apply the same concept to these two fractions individually, and you get the result. So that means if I want to find the value of A plus B plus C over X plus Y plus Z, it's just the same as this is just a scalar multiple, right? It is just like the constant we're scaling by. So it's, the first coordinate of the first vector over the first coordinate of the second vector, or the ith coordinate over the ith coordinate of each corresponding vector, or sequences if you want. So let's look at what we had again, right? So what was the problem again? Okay, so let me copy this over. Sorry, I was thinking in my head. Yeah, so someone said, I think it will be 5/6. Yeah, or it's either 6/5 or 5/6. So, because each of these is a scalar multiple of each of these. So A over X, maybe it's K, right? So that A is K times the value of X and B is K times the value of Y. So then we can just substitute, right? So this becomes K squared X squared plus K squared Y squared plus K squared Z squared. And then the Cauchy Schwarz says that this times this equals, well, this is AX plus BY plus CZ squared. So, this value, it was 25. This value was 36, right? So I think K, we just need to find the value of K, which is A over X, which is what the answer is. So yeah, X would need to be multiplied by, X squared would need to be multiplied by 5/6 twice to make, we can factor out the K, right? K squared times the sum of the X squared equals X squared plus Y squared plus Z. So if this is 25, sorry, and this is 30, then, we can just divide and see that Is it k equals 36? Yeah. So k equals 6/5. Is that? Hang on. Let's see. Oh no, sorry. I have it mixed up. Yeah, it's 5/6, right? Yeah, did I? So yeah, each a is 5/6 of x. We can make a 5/6 of x, b 5/6 of y, and c 5/6 of z, and this will be 25, and this will be 36. So yeah, that's fine. So yeah, 5/6 should be the answer. So yeah, I always flip inequality signs and negative, positive signs and reciprocals of fractions, unless I think about it really carefully. So yeah, this is a problem at ARMA, which is this round was computational, I think. So even though it doesn't say anything about an inequality, it happened to be the equality case of a common inequality. And that lets us deduce so if you're familiar with the equality case of Cauchy Schwarz, then this problem looks, it's very tractable. Otherwise, it's what the heck, there are 6 variables and 3 equations, right? Okay, so, I think this is good enough for today. I don't want to overtire myself, so I'll call it here for today. Let me know if you guys have any questions. Else I'll pause the recording. I'll stop the recording.